Hello all, can everybody hear me fine? All right, perfect. I'm sorry I can't see you all very well. The light is so bright. I never realized it was this bright. So like Frank had mentioned in this session called Advanced Technology session, we're going to be talking about, so far you've heard about the various hardware resources that Nautilus offers, including CPUs, GPUs, and memory. Now we're going to be focusing on other architectures of hardware, other resources that are available there, and how can users use them, what sort of use cases they service, and other specifications they have, and give you more information about them. And we're going to start off talking about FPGAs. So FPGAs, they're sort of the card that everyone is at least intrigued by, everyone is interested in. I'm just going to start off by briefly introducing what FPGAs are and how we deploy them on Nautilus. So FPGAs, normally we have our processors like CPUs and GPUs, they're general purpose. Whatever you throw at them, they're the tasks they're doing. In an analogy, you can think of them as a Swiss Army knife of tasks. So whatever processing tasks get thrown at them, that's what they're there for. So they handle a wide variety of tasks, but they don't handle them in an optimized fashion. This is sort of the motivation and use case behind using FPGAs, where in the same analogy, you can call them custom-built heavy machinery. So they're programmable hardware. You're programming hardware designed to do a specific job really well, designed to give you high throughput. So you're processing large amounts of data very fast. You're crunching your inputs into outputs in very high throughput and low latency, which means the cycle time between crunching your input, getting your output is very low, in the order of nanoseconds. And they're very energy efficient. So I think the FPGAs we have, the ones we talk about primarily on the cluster, are the Xilinx Alveo U55C FPGAs. Their typical power consumption is roughly 150 watts. And they offer flexibility in terms of them being programmable and reprogrammable hardware. So you can call them custom rebuilt heavy machinery because that's where the name comes from. So FPGA is short for Field Programmable Gate Array. Field programmable means they're as the name entails, it means they're programmable in the field, as in not in production, after deployment. After they're installed, users can come in, program them fully to the wire level, to the hardware description level, to do their specific tasks and deploy them to do their workflows. And they're gate arrays in the sense that they are arrays or grids of logic gates that can be programmed on the wire level to achieve that full programmability. So these are the cards we're talking about. This is a picture on the right side so you can get a rough idea of what we're talking about. They're full height, double width, so they sort of block the slot behind them, and they're half-length cards. The main interesting thing about them is that they have two QSFP 2800 gigs per second per port connections. So these FPGAs are fully programmable as SmartNICs, Smart Network Interface cards. And they fully support P4, which is a packet processing C-style language that allows for very easy packet processing. So with that, and with them being actually on a PCI card that supports Gen 3 16-pin, they offer very high bandwidth both for as Ethernet function and to the host they're installed on. So in Kubernetes terms, on the node, the physical node they're on, the pod that the user is provisioning, you can make use both of the Ethernet ports and the PCI connections. And that comes in handy in both high-level synthesis applications. You can make use, so high-level synthesis applications where you're offloading your compute tasks to the FPGA from whatever science domain you're coming from, whatever application you have. You can make use of the Ethernet connections if you program them to do so. Also, in SmartNIC workloads, you can utilize software, for example, like DPDK. So even in a network fashion, your packets are coming into the FPGA. You have full autonomy. You can control the flow of the packets. So you can, for example, packets can come in and out from the host and the card. So you can, for example, send the packets from the Ethernet to the host through the CPU. And of course, other specifications, like you see, these cards have high bandwidth memory, so they have HBM2 memory. 16 gigabytes at its bandwidth is 460 gigabytes per second. So that makes them very useful for all sorts of science domain applications. And there's plenty of use cases for FPGAs. Like we mentioned, they're fully programmable. So in programming those FPGAs, you can write C++ code that you can actually compile and run on the FPGAs. So there is no limit or enumeration of the use cases that they might have. It's sort of you're optimizing a workflow. So it comes down to the use case, whether or not it's more optimized to run it on an FPGA as compared to other architectures. But there's two main interesting workflows that we would like to talk about. The ones that we use the FPGAs for, both in research and in deployment, and that other users on the cluster use them for as well. And we covered both of those workflows in the tutorials on Tuesday. We have the recordings. We're going to be polishing them soon, and we're always more than happy to always introduce more users to those workflows and provide them with documentation on tutorials and content on how to reproduce those workflows and do something similar. And the first one and the main interesting one is machine learning and AI acceleration. So HLS for ML is a framework that converts machine learning models into FPGA-ready code. So it goes from a very high level, from the top PyTorch and TensorFlow models, and goes through all the process of synthesis until you have their high-level synthesis designs that can be compiled into bit streams that can be loaded on the actual FPGAs to do inferencing workloads. So the FPGAs can be used for inference and loading neural networks on the cards themselves. And one interesting thing is that this is fully open. It's open source. It's publicly available, and it's been tested on the cluster, and it is very reproducible. And the other use of the FPGAs is using them as SmartNICs, which is what we're gonna get down into details in the next slides. So like we said, you can make use of the 2 ports, and you can achieve high bandwidth for a variety of use cases. And we're gonna mention one where we use the FPGAs for our experimentation. And of course, to achieve that P4 programmability, we make use of the ESNet P4 SmartNIC tools. So the ESNet P4 SmartNIC tools, it's a stack of tools that is publicly available. You can just go on GitHub. If you go github.com/esnet/esnet-smartnic-hw, which is short for hardware, you can find the main repository that sort of explains everything. And the folks at ESNet have made the readmes for all those repos to be very easy to follow, very easy to reproduce. And in our documentation, we've also provided our examples of how you can replicate the exact same workflow on Nautilus and on the FPGAs that we provide. So the tools, essentially, in the very summed up fashion, what they do is they provide you with all the set of tools, everything you might need in a prepackaged, containerized fashion. So it's almost as easy as plug and play for P4. So P4, like we said, it's C-style. You write your packet processing logic. From there, you go on to loading and onto the FPGA with plenty of resources, including DPDK. So DPDK is short for Data Plane Development Kit. Very shortly, it's a software application that allows you to bypass the kernel to achieve high bandwidth and communicating with the FPGA through the PCI host without going through the kernel. And PackageGen. PackageGen is a DPDK application. It allows us to generate traffic. So not theoretically and practically, we can generate traffic, tell the CPU to generate traffic through DPDK, tell the FPGA to generate traffic, and send it through the ports, which is very useful for testing and deployment as well. And it also packages all the Vivado, Vivado is the software tool that is needed to run the FPGAs provided from Xilinx. It comes prepackaged with the ESNet P4 stack. And the main important thing here to mention is that in SmartNIC workloads, if you want to compile anything, you need licensing from AMD or Xilinx. And normally that licensing is commercial, but we have provided a floating license server on Nautilus that comes preloaded, as we're going to explain in a second, comes preloaded on your instances. So it's fully compatible with the ESNet SmartNIC stack. You don't even know it's there. You don't even have to know that it's there. When you load up your workflow, like we're going to show you in a second, everything comes preloaded and your license is already there, so you can successfully compile whatever you want. And of course, it comes with all the testing tools and debugging tools. So It's not write your software tested on the hardware. There's a whole series of simulations and whether behavioral simulations or it's completely software simulations that you can run to simulate how that behavior would be on the actual FPGA. And we provided a quick link. So docs.nrp.ai is the link for our documentation. If you go on there, you'll find all of our documentations. Inside of our documentations, we've listed how to use the FPGAs in both workflows, and and how to provision them and use them in fully. So the way they're provisioned on Kubernetes, so the FPGAs are recognized through the device plugin as a Kubernetes resource. So if you go on the FPGA nodes, you can find them if you type kubectl describe the node, you'll find them as a resource. So it's amd.com/the shell that the shell is the image. So it's the shell that the FPGA is running. As you can see, this is one example node that shows 4 FPGAs available. And if you would like to request FPGAs, you can simply directly do that in your YAML. So it's a matter of just requesting the FPGAs. I know a lot of people use the web page to see what resources are available. So if you go on portal.nrp-knowledge.io/resources, you'll find the spreadsheet for all the real-time available resources. You'll find there that we have columns for FPGA free and FPGA total. So you can sort and filter through FPGAs and find nodes you want to land on. And of course, this approach is ideal if you want autonomy, you want to do it by hand, you want to go through the Kubernetes approach, and you want to deploy it in your namespace, get that granular control. But the thing here, and this is me going off of on a tangent here, talking more about software, is that we have provided with a much simpler tool that provides you with everything you need to provision FPGAs, as well as do much more cooler stuff even without having to know Kubernetes and having to go through all the terminology and understand how everything works, and getting through that barrier into getting successful deployments, which is Coder. So Coder essentially is a web service. So it is a website. If you go on coder.nrp-knowledge.io, Coder is a website there that you can use your CI logon. You can just click on OpenID Connect, and that's it. You're logged in. You're inside Coder. So Coder, the simplest way to think about it is it's sort of a GUI wrapper for starting Kubernetes pods without having to know everything. So once you start it, it takes you to workspaces. And you can see here, so this is, for example, this is a screenshot of my Coder interface. You can see here the workspaces I started and the templates they use. So when we say workspace here is the equivalent of a pod. But with the extra that this pod comes preloaded with a persistent volume claim. So your home folder in that pod is persistent. You're not going to lose the files in it. And those workspaces are built by picking a template. And the template here is the image you're going to use. So the Docker image, the flavor of OS with the software tools that you're going to use, plus other configurations. So like we said, as you can see here, there's a U55C FPGA Vitus workflow. If you pick that one, it will come preloaded with the license server that we talked about, purely because you picked that template. And you can see here we have 2 templates for FPGAs. We sort of have the distinction between the 2 workflows because of the differences between them. So we have the U55C FPGA Vitus workflow. Vitus is another software tool. Software, you can think of it as an IDE. So we have Vitus and Vivado. They're both provided to all users through Coder. So you don't have to go reinvent the wheel and reinstall the software and create PVCs and whatnot. We have one shareable PVC that has the tools that all the users share. And whether you pick this template or this template, it comes preloaded with it. And we have the ESNet one because this template comes preloaded with all the resources you need for the ESNet SmartNIC stack. So all the things you have to set up to have the stack up and running, all the Docker images, because it's a Docker Compose stack. It has many images it runs. It has many systems that need to be in place, many configuration files that need to be configured in the correct way. But if you pick the template, it's as easy as going into the template, finding your system already there, finding the P4 file that it is going to compile, and just edit that one file, and then run one command, and that's it. you have your system up and ready to be loaded on the FPGA, which is also one extra command. So in 2 commands, you have your SmartNIC workflow. And like we mentioned, if you go through the coder way, you don't have to deal with knowing how to request those hardware resources. And you have plenty of cool features. So there's big incentive to use Coder here. And one of them is that Coder offers custom Kubernetes workflows. So in our example, workspaces, the way we use it, our public Coder instance, a workspace is a pod. But since it's programmable with Terraform, you can specify a Terraform schema that basically defines what you're deploying. It doesn't have to be pods. If you have more intricate designs, you're launching, let's say, deployments or VMs or jobs, you can also do it through Coder, through a GUI, so users can deploy their HPC jobs without actually having to learn Kubernetes. You just have to sort of specify the recipe of success that you have, and then they can follow it without having to deal with namespaces and YAMLs whatsoever. And one of the other cool stuff is that it offers remote desktop in a browser, so it's very useful in interactive coding session, so interactive development sessions. You don't have to set up, let's say, no VNC or sulkies and going through all the steps, just clicking a button and your desktop is there. And the main highlight, the reason Coder users love it so much is that because it has native VS Code desktop integration. So a lot of the users, especially the ones who are not very comfortable basically working inside the pods, a lot of the, or on CLI, a lot of the users prefer to have Visual Studio Code desktop running locally on their machine. And with Coder, it's, as you can see here on the top image, this is what you see when you launch a workspace. So VS Code desktop, it's just a click of a button and you're on your desktop. You have VS Code. On the other hand, there's also Code-Server, which also has a VS Code icon. The distinction here is that this one runs VS Code as a service, as a web service inside your pod. So when you click this one, it opens a browser window, as you can see it here. So the top right image, that one is running from my pod, and the one below it, that one is running from my desktop. So you have both options. And there's the matter of connecting to the pod. So not all users are comfortable with doing kubectl exec, and not all users are very comfortable with connecting to the pods. Coder already sets up SSH for you, so you have terminal in a window. That's it. You can also use the Coder CLI. It also provides native SSH, so it's if you use the Coder CLI locally on your machine, it's just a matter of typing Coder SSH, then the name of your workspace, and that's it. You're inside. And lastly, and this is a very cool feature of Coder, is that each user on Coder has a private SSH key, and that SSH key cannot be seen by anybody else, even the administrators. So from our side, we cannot see your own private SSH key. That SSH key is injected into every single pod and VM or anything you start inside of Coder. And this is a very handy feature because and there has been many instances where users forget to back up. A lot of their information is gone. A lot of their code is gone. They want to preserve their progress. They don't want to build a pipeline to preserve that progress. It's just a matter of putting that SSH key, let's say, into GitLab or GitHub, and then you can just deal with your repositories, pull, push, do whatever from inside Coder without having to reconfigure every time. And this is also sort of a shameless plug here, is that we have deployed Sulkies on Coder. So Sulkies is also a remote desktop client that allows you to do either CPU or GPU accelerated remote desktop environments, which are blazingly fast. They're very smooth. We've had a much more positive experience with them as opposed to no VNC in terms of quality. And the notable thing here is that it also streams audio, and it's directly native in your browser. So when you start a Coder instance, you have your remote desktop streaming with audio. And the general template, it's one of the templates we've seen. We're trying here to copy as much as we can our public Jupyter Hub, which I'm sure a lot of you have used before. So like you can see here, the general template is made to be the most general template that you can specify. It has a lot of fields that you can specify where resources you're requesting and how you want your pod to be configured. And we've added our documentation. So a lot of users pick Jupyter Hub. You can also pick Coder, and we've added in our documentation similarly to how you can spin up your own Jupyter Hub, we've added documentation to how you can spin up your own coder in your own namespace. So it is an alternative that is there that provides an easier way of even dealing with your own pods and workspaces, and you can deploy it in your namespace for your own use cases. And that's pretty much it from the software side. So Coder is the software that allows you to provision FPGAs. And for anyone who is interested in using our FPGAs, we always recommend Coder so you don't have to deal with all the intricacies of requesting the FPGAs and configuring everything on your own. The other architecture we wanted to talk about is another flavor of FPGAs that we have. And we have 24 of those cards that are deployed on the cluster, and they are the Bitware 520 NX cards, which this is their commercial name, but the FPGA inside them is the Intel Stratix 10 NX cards. And those FPGAs are very powerful. They're marketed as AI accelerating HBM-enabled FPGAs. So another notable thing about them is that they have 8 gigabytes of high bandwidth memory. They have 32 gigabytes of DDR4, and they have 6 QSFP28 100 gigabit per second connections. Similar to the Xilinx FPGAs, they have Gen 3 PCIe 16-pin. And like we said, these cards are made to be also, aside from being FPGAs, and they're being FPGAs, they're also AI inference cards. So they benchmark at 143 integer 8 trillion operations per second, which is very comparable to a modern GPU. Maybe not the top ones, but not the top data center cards, but it's very comparable to a GPU. And considering that we have 24 of them, the possibilities that you can do with these cards with respect to AI applications is very massive. And their power consumption as a maximum is 225 watts. If I remember, typically they're 175 watts. I could be wrong on this figure, but that's what I remember. And in terms of software environments, so they're very similar to the Xilinx FPGAs in terms of them needing software. Like they require Intel Quartus Prime Pro, which is also something we provide over Coder, and they're also fully programmable using SYCL using Intel One API support. And now this is the interesting part here. The main thing we want to talk about today is the Qualcomm Cloud AI 100 cards. Actually, we have the Qualcomm AI 100 Ultra cards. So these cards, they are high-performance AI inference accelerators. We just deployed them. They're very fresh. They're the new cards we have. They're highly optimized for all sorts of generative AI models, especially large language models. And some of their specifications that they have 576 megabytes on die SRAM, and they're power efficient. And these ones are comparable to GPUs, and in a lot of instances, they outperform GPUs, especially in the use cases that they're made for. And we're just gonna talk a little bit about how they work. So each card here is one PCI card. The terminology used here is that each card has 4 devices. So when we say device, we mean 1/4 of a card. So the card hosts 4 individual devices. And those devices inside of the card have peer-to-peer access. So whether you use 1, 2, 3, or 4, or however combination you want, there's no bottlenecks. It's the same speed. And each one of these devices is capable of hosting a large language model. If we speak in terms of large language models, roughly for each one of them is capable of 25 billion parameters. And each one has 16 NSP cores. So when we're talking about processing power, we measure it in terms of neural signal, I think it's neural signal processing core per card. So the card itself has 64 of them because it's 4 times 16. And we have 8 of these cards deployed on one node, and the node is called NRP-AI-100-01. That is our node. We have 8 of these cards. And like we said, each card has 4 devices. So what you'll see on the Kubernetes side is that we have 32 devices. And those devices are already available. They're on the node and they're on the cluster, and users can see them and can request them and can start deploying their inference jobs on them. They can start deploying their LLMs on them. And of course, when users request them, let's say this is, for example, if a user requests 5, that it doesn't necessarily go in order of cards, because the cards themselves, each 4 cards, they're on a PCI switch on the host, on the node itself. So however the devices you're requesting are spread, there is no bottlenecks. You basically, for your workloads, it's not gonna show any difference where they're at. So we have 32 individual devices here, each one at roughly 25 billion parameters that can be requested either individually or as in a combined fashion. And let's say you're deploying somewhat of small large language models, so medium language models. You can request, so you can only get multiples of a device. So the least you can go is 1 device. But once you requested, you're inside of your pod, you have 16 cores. So you can also deploy on these cores individually. And some of the uses, so some of the neural networks that are out there that are tested on those cards and that are publicly available for users to test out, there's plenty of computer vision models here. I know a lot of you might recognize YOLO. It's very popular in terms of detection and classification. There's plenty of models that all of these models listed here have been tested and are fully functional and available. Other models, it's just because those cards are very fresh. We just installed them on the cluster. I don't think anyone else has them yet deployed in the scale that we have. So it's just a matter of testing transformers, testing the different models. Other stuff might work. It's just that no one has got a chance to test it yet. So everybody has them now, so we can just go on the cluster and test different stuff. This is an example of how we tested stable diffusion. So this is the DESI diffusion v2 model. This prompt was a cat that is fed with a hat on a mat, just to test out how the cards work, how fast they are, and how the model actually produces images. And the one on the right side was just nature. So this is actually running on the cards. This is us testing the cards. This is 2 different prompts. So this is beach sunset, and you can see here where the model doesn't get it quite right and starts hallucinating. This is a dinosaur in front of a tree, and you can see the dinosaur and tree are 1 in here. Yeah, this is running on the QAIC cards on the cluster, the ones that we have. And one main thing also to mention here is that the cards are fully programmable as accelerators with C++. And there's the QAIC Compute SDK that comes already preloaded on the images that we have, so users can go on and program them in a manual fashion with C++, similar to how CUDA developers do on GPUs. And LLMs, this is also running on the cluster. So this is DeepSeek, where we grabbed the DeepSeek R1 distilled into a Llama 70 billion parameter model, and we tried it with a couple of prompts. This is actually very fresh, so we ran these prompts just last night because we just installed the cards and we were hoping to get something in so we can showcase it to you. And you can see here how the model did. This is an example with all the hype that DeepSeek has been getting. I don't think it's very good at poetry. The second prompt is a Kubernetes poem, and it's sounding just like normal text. There's nothing that says poem about it. But it did get the first one right in terms of where the novel Rainbow's End setting was. And of course, so we haven't had a chance to test the cards out yet. Like we said, they're very fresh, but we're hoping to test all sorts of generative AI models, all sorts of LLM models, hopefully even build pipelines that go from model to achieve more of general AI. I don't want to say the term AGI, but custom built generative AI models. And we're hoping you as a community, you can test out the cards, you can tell us where they're good, where they're not good, and how they perform, how they compare to GPUs. One thing just to mention here for people that like graphs and data and how it goes. So we monitored the pod that did all the work on Grafana, and this is what loading the model looked like. So you can see here, you have 2 lines. Each line is a different instance of loading the data. So you can see memory usage for loading 170 billion parameter model it came close to 640 gigabytes on the host. So we were requesting all the memory on the node to achieve those results. And you can see once you load the models, it sort of goes into the downfall. But you have to load the models, and that is a very memory intrusive process. And in terms of CPU usage, it does peak, but that's just in one step of the compilation process. Other than that, it just goes into downfall and free fall. And oh, perfect. So that won't be an issue anymore. You'll have double the memory. And that's pretty much it. I don't know if we have time for questions. Does anybody have any questions? No.
So this is sort of a mixed question to you and Dima. So in principle, this could now be made available with deep seed for all I care for Carl to play in his course via the light LLM. Is that true? Yeah. So we literally could make that just available for people to play, and it might be easier for people to play with as an LLM than to play with as a hardware environment.
And it's consuming resources because we run single LLM that people can use together rather than everybody's running their own version of it.
Eric.
Can you put like the nice models in a shared read write so that everybody can find them and people don't have to make copies after copies of the same?
Yeah, that's
Yeah.
what Frank is talking about. We are now running a thing called Light LLM. That's a proxy of the LLMs, and you can register or just use L11. And there is a bunch of LLMs we already provided. You just create your own token.
And you have some shared read write where any user can access.
Yeah.
Okay.
That's
That's
what you should, right? But you
as
can
well, but it's nice to have not everyone on your system downloading these giant models.
Right. Yeah, that's the idea.
So, Dima, why don't you have DeepSeek in it yet?
It's there.
No, in
Oh,
Light
yeah.
LLM.
Yeah, that's another day.
So maybe that we can take this offline, but maybe that is the way to make this available, because it's probably going to be too high a lift for most people to actually do program against it.
Yeah, so the tools that are needed to host the image, the models with the ones that we have are compatible with the cards. So
Cool. Thank
we
you.
should be all set. And not to spoil Dima's work, but soon everybody on Jupyter will have the AI features that we've seen throughout the workshop.
Cool. Any other questions? Good. Then you off talk.
All right.